Okay, this first video is going to be over the history of microbiology. I'm going to try to keep these short throughout the entire lecture. Not going to cover every single thing in a video, but just try to talk about maybe more of the complicated things. But anyway, if you're going to study microbiology, you do a brief history of all the older, more prominent figures in microbiology. So obviously it is the study of microorganisms. Most are unicellular and exhibit the properties of life. Not all are unicellular. Worms, for instance, helminths, are not. They're multicellular, so are fungi. So let's start here first. Now, up until the 1600s, there was no study of microbes.
And that's the bottom line.
This person here, he was an important person in micro because he basically came up with the theory and then the application of a microscope. So this is that lesson that doesn't really have any questions. It's got some information in here, but that's it right there. That is his first microscope. Obviously you can tell it's not really complex, but he was able to see some of the very first observations of what are called cells. Now his term actually stuck, and he was looking at cork pieces, and cork, the cells are square. So he, excuse me, he called those units that made up the piece of cork that he was viewing as cells. Other people try to come up with names, but his obviously is the one that stuck, because nowadays we refer to the smaller, a cell is a unit that makes up a tissue, and then tissues make up organs, and then you have entire organisms. So that was his contribution to early microbiology. Robert Hooke, he actually invented the microscope. Now this guy, Anton Leeuwenhoek, now he was one of the first people to actually observe live animals, and he would take things out of his teeth, other body fluids, observe them under a microscope, and like it says here, first person to observe living organisms under magnification. He called them animalcules, which obviously that term did not stick. We don't use that term nowadays, but that was really his contribution. He was the first person that really saw things that were moving around. He would take things from his teeth and he'd make a presentation out of it and look at it under magnification, and he could see things swimming around and moving around. And that's him right there. All right, Mr. Ignaz Semmelweis. We cover him in lab a little bit. He always looked like this. He always looked constipated. He was a surly guy. He screamed a lot. He wasn't a good communicator, but his contribution to the micro world was huge. Basically, this streptococcus infection, puerperal fever, very contagious, spread by direct contact, fatal, and you're talking about, this is 1847. Penicillin was not discovered till 1929. So people who got sick back in this time of bacteria infections, well, chances were, I mean, it was 50-50 that you weren't going to make it. It's not like nowadays. I mean, medicine in our present day is very advanced compared to what these guys were dealing with. So basically, I'll summarize what he did. And you can read through this, he actually, back in his time, people who would go into a hospital to deliver babies or were sick, well, they were getting what are called nosocomial infections. Those are infections you get in the hospital, and they were dying, especially women who were giving birth. Babies were getting infected, the women were getting infected. And so what he started doing, he started making his medical personnel, people that were underneath him, wash their hands between patients. And by doing so, he was able to document a huge decrease in the disease and the spread of disease in his particular area of the hospital that he worked. Like I said, the problem is he wasn't a good communicator, and I don't mean to bounce back and forth here, but there he is. That's kind of a picture showing people washing their hands and everything. But the problem is he wasn't a good communicator, so he was very confrontational, and people didn't take him seriously till after he died, of course. And he actually was committed to an asylum, and he died of puerperal fever, of all things. But that's what he is. He's very, I mean, he really invented hand washing. This idea of transient flora and you removing transient flora from your hands when you wash your hands. And even today, medical personnel are supposed to wash their hands when they come into a room. All right, the next guy, Louis Pasteur. Now, if there was such an analogy, he was the Michael Jordan / LeBron James / Tom Brady. You know, he was that guy in the science world. He was a French chemist. That's him right there. And he did so many things in microbiology. We're only going to talk about a couple, but he came up with pasteurization, the heating of fluids to kill pathogenic microbes. So not only does it not make you sick, but the fluids don't spoil as easily as they would have. But I'll tell you his story and I'll summarize it. But during his time, this is one of the things that he is credited with, this idea of spontaneous generation. During his time in the 1860s, scientists, people thought that if you got sick, that something just spontaneously generated. Even when it would rain and you'd see frogs coming out of the ground in the rain, they thought that was spontaneous generation. In other words, there was no idea that there was actually an organism that was there and causing a person to get sick already. Nothing was spontaneously generating out of the air. So what he did, now, I have a few limited pictures of his accomplishments, and I'm sorry the writing for that is so small. But, yeah, you can see him here, and I have his flat. There we go. Okay. So here's the thing. So in science, you do experiments. If you take chicken broth, which is in the bottom of this thing, if you leave chicken broth out at room temperature, it will look clear. After a few hours, it's going to look cloudy because there are microbes that are already in chicken broth. And if you leave them out at room temperature, they're going to multiply over time. Back then, that was not understood. And so what he started doing, like I said, he came up with pasteurization. When you're heating fluids to kill microbes, what he demonstrated here was this is one of his flasks. See, he heated the end so it's bent like this. And when he initially started trying to disprove spontaneous generation, people would take this chicken broth and leave it there for hours, and then of course after a few hours or a day it's loaded with microorganisms, and they would say, look, that's spontaneous generation. There was nothing there before, and now there's millions of microbes. And so what he did, he would heat up the fluid here, which would kill all the microbes that are already there, and then this little design of his flask, these bins, they actually prevent microbes from the air from getting down into the chicken broth. So once you boil this and kill all the microbes, and you prevent any from contaminating it, it's going to remain sterile. And by doing so, he disproved spontaneous generation. He left, you can leave this out. In fact, this is one of his in a museum, which I believe is his house. It's been there 200 years, plus, over 200 years. And, well, no, math is not a micro person thing. Over 100 years, put it that way. It's been sitting there and it's still sterile. So he disproved spontaneous generation. He disproved the fact that if you kill microbes that are there and you prevent the entrance of air or microbe, well, in this case, air could flow through here, but the microbes couldn't. Because at some point, people were saying when you would cut off the air from something, they would say, oh no, spontaneous generation needs air for life and all that. So he basically disproved spontaneous generation. This kind of setup allows air to flow through, but it prevents the microbes. They can't make these bends right here. So whatever's inside remains sterile. Very famous for that. And he did come up with pasteurization as well. And you can read through that. And he also did come up with what's called the germ theory of disease, and that is that you can link basically an organism with a certain disease like anthrax, tuberculosis. So he's a very famous guy. All right, Joseph Lister. That's him. Just look at his last name and think automatically right now, what do I buy that's related to brushing my teeth that has the term Lister in it. So basically, he was the first guy that sort of used chemicals to treat infection. And his first chemicals were very strong. It's basically what pine sol is made of. And he would spray them on like surgical fields when they were working on people. Here, you can see him there. See him spraying this is a machine, this mixture over someone having surgery, which back then, oh my goodness. But yeah, and he was preventing surgical infections. So back then, obviously, infections were a big deal. And of course, post-operative surgery infections were huge because you can see these guys don't have gloves on. And you're opening up a person's body and you're putting your hands in there and do all those things. And most likely didn't sterilize instruments. So that's what he's famous for. He used chemicals to treat infection. So wound infection, blood. Yeah, phenol carbonic acid, super strong stuff. Would burn like crazy. But yeah, it kills microbes, absolutely. But yes, he's also today, his family, Listerine, is based on Joseph Lister. John Tyndall, what is his contribution? So as we go through all this, we'll talk about all these things, but there are certain microbes that are sporeformers. That means that when they start to perish, they're in dire straits, they can form a spore. And a spore is a dormant, resistant structure. They're very hard to kill. And he came up with a way of killing those spores. Well, staining them and also killing them. But it's called Tyndallization. A method now was devised to destroy spore-forming bacteria. If you have a spore former in your house and you're cleaning, you're not really killing the spore formers, you're wiping it off. But nowadays, there's a term that's autoclaving. It's using pressure and heat to sterilize instruments. Not everything can withstand that. But he came up with that. And the idea of this vegetative form is when it's active, believe it or not, which was heat sensitive. Heat sensitive meaning it was killed by heat. And then there's a heat-resistant form, which was called a spore. Koch, that's how you pronounce his name. Edward Koch. And he came up with what are called Koch's postulates. And here they are. He studied organisms and disease, and he was able to link organisms with a certain disease. Back then, that was not known. So these are actually used today. An organism must be found in all animals suffering from the disease and not in healthy animals. That's probably a no-brainer there. You must be able to isolate the organism. So you take an animal's blood, you isolate something like anthrax on a culture petri dish. The organism should cause disease when introduced into a healthy animal. Absolutely. So you take an animal that's sick, you isolate an organism that's making it sick. If you inject that into an animal and then it dies, and then if you basically take the blood again and re-isolate it, and you find, oh, there it is again. There's the same organism. That's how you can link diseases to certain microbes. And that's what he's famous for. These are called Koch's or Kochs. I've even heard, I've heard more than anything Koch, but these are called his postulates. And yes, he worked with anthrax, tuberculosis, all those kinds of things. Jenner, interesting story, and I'll try to keep this short. He's credited with vaccination. He worked with cowpox, and which cowpox is a condition that affects cattle, obviously, but back in his time, smallpox was a very virulent, meaning strong virus. Smallpox is fatal in 5 to 6 days. And so he actually invented vaccines. Now, he died before he could finish his work, and Louis Pasteur actually finished his work. But Edward Jenner, and there is Mr. Tyndall, there's Koch, and here is Edward Jenner. So to summarize his work, he noticed, and some of his story has some pretty big holes in it, but back in his time, smallpox was wiping out thousands of people. And he noticed that people that worked around cattle were not getting sick from smallpox. Well, cows get something called cowpox, and their face breaks out, which smallpox causes that with humans too. You get it looks like a bunch of bumps, rash kind of thing. It looks terrible. And he noticed that the milkmaids, people that milk cows, were not getting sick. So he started doing some experimentation with the cowpox. And at some point, he inoculated. Okay, so basically, he took some cowpox and he inoculated a person that works around cows with cowpox. They got sick. Of course, cowpox is not fatal to humans. And then he actually gave this person smallpox after this person had recovered and basically the person didn't get sick from smallpox. It's an idea of what is called acquired immunity. Kind of popular nowadays. But yeah, if you get vaccinated for something, your body's going to develop a response to it. And the second response to the same microbe or disease is going to be much stronger, and most likely you're not going to get it. So he also at some point inoculated his son with cowpox. And here's the thing, cowpox causes an immune reaction that is the same as smallpox in humans, but cowpox is not fatal. So basically, it's like getting vaccinated. And at some point, he inoculated his son, which that's interesting. But yeah, his son survived smallpox, and he would actually go town to town with these cows and offering to vaccinate people against smallpox for a fee. So, and like it says there, he wasn't really aware of why it was working. He just knew it was working. So, Vanca is Latin for cow. So you think about vaccination, the term, it actually means encowment, of all things. And just a few more. Eli Metnikoff, another interesting story. He studied white blood cells. There he is. There's Mr. Eli. You can't see in this picture. It's not very big. But he studied white blood cells, and there are white blood cells that eat foreign cells in your body. He's the first guy to study that type of immunity. And how he discovered that, he had a thing for starfish, and he also married a lady that had, I want to say, 12 children. Oh, so he had a lot of patients as well. But a couple of the kids, I guess his stepkids, he used to keep starfish. They took the starfish out. One of the starfish is out of their wherever you keep a starfish. I don't think it's scampering around the backyard, but you take a starfish out. They took one of his starfish. They put it on his desk, and they put thorns through the starfish and pinned the starfish to his desk. They crucified the starfish. Of course, he finds it. Of course, he gets upset. He removes the thorns. The starfish survived. But a few days later, he noticed everywhere where there were thorns, there were white areas and pus around in the starfish where the thorns were. And so he started looking at that fluid, and then those were white blood cells. So he discovered that. The crucifixion of his starfish allowed him to discover a type of white cell that responds for immunity. I believe last two, no, we have three more. There's Metnikoff. Paul Ehrlich was another guy that he sort of came up with this idea of using drugs and chemicals to treat disease. He treated syphilis patients with mercury from the bottom of thermometers. Compound containing arsenic. If you don't know anything about syphilis causes lesions, the type 2, the second stage does. And he would smear basically mercury from thermometers into those lesions, and they would dry up and go away. So he was kind of the first guy to use, they called it chemotherapeutic drugs, or drugs to treat disease. Rivers was a guy who studied viruses. He came up with the same postulates that Koch did, except his pertained to a virus. Virus must be found in diseased animals. You can isolate the virus, which is a little bit harder to do. He came up with a way of filtering things to isolate the virus. The virus should be introduced into a healthy animal and then should be re-isolated. We got a few extra blanks there. This stuff drives me crazy. Anyway, so that's anyway. So Rivers studied viruses. Koch actually studied other microbes, bacteria, things like that. Okay, last guy for this video, Alexander Fleming made probably the most important discovery, and there's a virus, once again, pretty popular nowadays. This is him, Alexander Fleming. He discovered penicillin, and his story is, and there he is. See the stack of Petri plates in the background? He was a scientist, but he studied a lot of fungus, bacteria, and one day he noticed on one of his Petri plates, now, usually he had somebody come in and clean out his office. The person that usually did it was sick, so he was cleaning it out himself. And he was throwing away Petri plates, and he noticed on one of the plates that this white substance, looked like a fungus, had grown on the plate and had killed everything that was on his Petri plate. Everything meaning bacteria that he was growing on the plate. And so he started doing some experiments with it. The fungus was called a penicillium, and sure enough, he came up with, he finally figured out that it produces an antibiotic, which is, antibiotics are chemicals produced by microbes that kill other microbes. And yeah, he was able to isolate penicillin, the drugs, from that. And it's called the magic bullet because penicillin does not affect humans. It only affects bacteria, the cell wall of bacteria. So during his time, 1929, life expectancy after this discovery went up 20 years, maybe possibly. In 1900, average life expectancy was about 40. And of course, nowadays, it depends on if you're male or female. If you're male, I want to say it's 76. If your average lifespan, if you're female, it's close to 80. But yeah, that's what he did. He discovered penicillin, and he didn't market it and try to sell it for a huge profit. You know, he could have probably become richer than anybody. But yeah, he's credited with that. Okay, well, I hope this helped. I'm going to make another video on the types of bacteria you find in microbiology.